In this class, now I am going to explain you differentiability of a function. Differentiability of a function. See, the first objective of this chapter is differentiability of a function at x equal to a, where a belongs to any real number and that a is the part of a domain of a function. Differentiability of a function f of x at x equal to a. See, what we are going to discuss, differentiability of a function f of x at x equal to a. F of x is a function. We have many more functions like algebraic functions, logarithmic functions, exponential functions, trigonometric functions, inverse trigonometric functions, composite functions, like many more functions we have. So this function may be any one of all those functions. Now, whether this function is differentiable or not at x equal to a, we need to check. What is the meaning of differentiability? Whether the differentiation of the function is possible or not, you have to check. Okay, whether the derivative of the function is possible or not, you have to check. You know, if the function is given y equal to f of x, so whose derivative is dy by dx, otherwise f dash of x. Actually, derivative is nothing but slope of a tangent, which is drawn to the graph of this function. What is meant by derivative of a function? Slope of the tangent, which is drawn to the graph of this function. You know, if you draw the graph of this function, we get like a curves. For that curves, you can draw the tangents, no? So this derivative represents the slope of that tangent. So here in this chapter, what you people have to do? So this is the name of the function, and a is one of the point in its domain where tangent is existed or not. If it is existed, if the tangent is possible, then it will get slope. So slope of a tangent belongs to a real number, you know. So whether that derivative of this function is possible or not at x equal to a, you have to check. Now how to check? Now I explain you. So what is first objective of this chapter? Differentiability of the function at x equal to a. Now let us check. See, draw the graph of this function. X, x dash, y, y dash, this is origin. Now, here I have taken graph of the function. I may get like this, y equal to f of x. Now take a point on the graph as a. If domain is a, respect to range will be f of a. You know this. So here, let us name this point as P. P. Now at P, I would like to draw a secant. So the secant is meeting the same curve at other point. Let us name this point coordinates as a plus h, and respect to range is f of a plus h. So the distance from here to here, a. So from here to here, h. A plus h. Then coordinates of this point will be a plus h, and respect to y coordinate f of a plus h. So let us name this point as a. Now find the slope of that secant. slope of the secant. If you find the slope of the secant, what do you get? You know, difference of y coordinates by difference of x coordinates. This is the slope of a secant. A cancel. So after this, keep this point here itself and rotate this PA in the clockwise direction. So like this, so you rotate. You get like this. Keep this point here itself and bring it to the down in the clockwise direction. So if you rotate like this, so observe carefully. From here to here I said to you h. So the value of h is decreasing. Whenever this value of h is approaches to 0, then the secant will coincide with this tangent. Whenever, see, bring like this. Whenever this h value is approaches to 0, tends to 0, this a will coincide with p, hence the secant will become a tangent at this point. So then what it will be? Slope of the tangent at p, f of a plus h minus f of a by h. This is called what? Whenever h approaches to 0, so this represents slope of the tangent at p. So we have rotated this secant from right side portion of a. So this h is approaching. So h is approaching 0 means a is approaching p, and a is going to coincide with p from right side part of p. Hence this is said to be right hand derivative of this function at a. What it is? Right hand derivative of the function. It is denoted by f dash of a plus. This is also called as right hand derivative of the function. So you people have to use this formula to find right hand derivative of that function at p. In the same manner, take the secant like this, and you know, from here to here a. So here let us name this point as b. So the distance from p to b horizontally like this, b small h. Total length is a. From here to here h, then this length will be a minus h. Hence the coordinates of this point b as a minus h comma f of a minus h. So now again keep this p here itself and bring b to the down. So like this will come when you bring this b to the when you bring the secant down. So this b is going to coincide with p, means h is decreasing. Whenever h decreases, slope of this secant becomes again slope of this tangent drawn at p. Are you getting me, students? So same, however I have taken secant right side part of p, same like you have to take left side part of p. Now slope of the secant f of a minus h minus f of a by a minus h minus a. So what is this? Slope of the secant pb. So now a cancel. Now m is equal to f of a minus h minus f of a by minus h. So this is said to be slope of the tangent at p when h approaches to 0. This is the slope of a secant pb. Now that is going to be slope of the tangent at p whenever h approaches to 0, means b is going to coincide with p. Then the secant will become tangent at p. F of a minus h minus f of a by minus h. This is called left hand derivative of this function at p, that is denoted by the letter f dash of a minus. So this is called left hand derivative. What it is? Left hand derivative of that function. I hope you have understood what is meant by left hand derivative of the function, what is meant by right hand derivative of the function. Okay, so remember like a standard results. Now see here, A, whenever it coincides with B, so that secant became a tangent like this. Now whenever B coincides with P, that secant became tangent. So both are coincides with this tangent, no? Okay, so that is called, so actually what it is, when LHD is equal to RHD, both are coincides with a common tangent at P. So both should be a finite result. Both should be a finite result, means a finite real number. Real number. If both will be given a finite real number, and at that point A, if that function is continuous, then you people have to say that function is differentiable at x equal to a. When do you say a function is differentiable at a? Function must be f of x is continuous. F of x is continuous at x equal to a, and LHD is equal to RHD, and both should be equal, and both must be equal to a finite real number. Okay, so whenever a function satisfies these two conditions, then you people have to say that function is differentiable at x equal to a. Compulsory that should be continuous. If the function is continuous, it may be derivable or may not be derivable. Sometimes that function is continuous but need not be derivable, need not be differentiable. But if it is differentiable, compulsory at that place that function is continuous. Remember this point also. If it is continuous, here at x equal to a, I am saying that it is continuous. At that point it may be differentiable or may not be differentiable. But sometimes, okay, see, if it is continuous, it may be derivable or may not be derivable. But if it is derivable, compulsory, that is continuous. Okay, I hope you have got it. Right. Now, when that function is not derivable at x equal to a, tell me. Till now what did we discuss? Differentiability of a function at a point. When we have to say that function is differentiable at x equal to a. When you have to say that function is continuous at x equal to a, you know how to check whether it is continuous or not. Left hand limit of a function is equal to right hand limit of a function, and both must be equal to a value of the function at x equal to a. Then you people have to say that function is continuous. Already you learnt this knowledge in the continuity chapter. How to check left hand limit of a function. You know, you have the formula limit h approaches to 0 f of a minus h, and right hand limit formula limit h approaches to 0 f of a plus h. Both must be equal, and both must be equal to value of the function. Then only you people have to comment that function is continuous at x equal to a. Okay, these are the standard formulas, but in the competitive track, so every time, so no need to apply this standard formulas to check whether the function is continuous or not. We have many more methods to confirm whether the function is continuous or not by the graphs and by sandwich theorem, like many more methods we come across. So okay, but some functions we apply the standard results and we confirm whether it is continuous or not. So sometimes we approach other methods to confirm whether the function is continuous or not. Okay, so we have some standard results also. You know, all the exponential functions and logarithmic functions, differential trigonometric functions, inverse trigonometric functions, polynomial functions, constant functions, all these functions will be continuous in its entire domain. By the standard results you can say. Okay, but now at present we are discussing differentiability of a function. But when you have to say a function is differentiable at x equal to a, there that function must be continuous. So you have to check whether the function is continuous or not. So to check the continuity of a function, you can approach your own methods. But these are the standard formulas. Whenever LHL is equal to RHL is equal to f of a, then that function is continuous. And along with this, you need to check LHD and RHD, and LHD and RHD both must be equal to a finite value, finite real number. Then you people can say that function is differentiable at x equal to a. I hope you have understood whether the function is differentiable or not at x equal to a. Now, when this function is not differentiable at x equal to a, tell me. Not differentiable. Not differentiable at x equal to a. Tell me. So, first one, that function, if it is may not be continuous. If a function is not continuous at x equal to a, this is one point. Not continuous. Not continuous at x equal to a. If it is not continuous, not differentiable. And second one, sometimes it is continuous but may not be differentiable. This is one case. If it is not continuous, not differentiable. And suppose if it is continuous, then you have to check whether it is differentiable or not. So now find the LHD and RHD. Both may not be equal. Both will be given a finite result, but both may not be equal. In this case also, that function is not differentiable. For example, f of x equal to sometimes both will be finite. Both attains a finite result, but both may not be equal. Now, LHD is not equal to RHD, no? Hence, what you have to comment? That function is not differentiable. And sometimes both will be attains a not defined value. Like you say it as infinity. Meaningless. Both will be attains a not defined value. So in this case also that function is not differentiable. See, for example, f of x equal to x power 1 by 5. Now comment on the differentiability of this function at x equal to 0. At x equal to 0. How do we check? This is continuous at x equal to 0. Okay? Is this continuous? Students, it is continuous, but it is not differentiable. If you want, you can check left hand derivative and right hand derivative. And if you would like to check whose continuity, you can. You have the formulas. Okay? Shall I show continuity? See, left hand limit What is the formula? Limit h approaches to 0. F of a minus h. A means x equal to 0. A. 0 minus h. So which is equal to minus h whole power 1 by 5. Now put h value 0. You know h is a very infinitesimally small value, and that too positive value, like very close to 0. 0.0001. Very small value. And if you substitute here, this becomes 0. In the same manner, check the right hand limit. RHL, just here you have to put plus. Now put their h value 0, which becomes 0. Already value of the function. Put x value 0. 0 power 1 by 5, which becomes 0. Now left hand limit, right hand limit, both attains 0, and value of the function 0. Hence that function is continuous. Now whether it is differentiable or not, check it at x equal to 0. At x equal to 0. Check the differentiability of this function f of x equal to x power 1 by 5. Now find LHD, RHD. LHD. So what is the formula? Limit h approaches to 0. F of a minus h. A value 0 means f of minus h. Minus f of a. F of a means which is going to be 0 by minus h. So what you are going to get? Minus h whole power 1 by 5 by minus h. Now if you simplify, minus h whole power, so a power m by a power n, which is equal to a power m minus n. 1 by 5 minus 1, which becomes minus 1 by 4 by minus h whole power minus 4 by 5 will come when it comes to the down. So what do you get, Amma? Minus h whole power 4 by 5. If you put h value 0, it attains minus infinity. Sorry, here minus power even number, which becomes positive, you get positive infinity. Because this is meaningless, mathematically not defined, which is nothing but, see here, you have to express with this symbol, not defined. That is one of the indeterminate value. So in the same manner, find RHD. RHD, what you have to do? Here you have to put plus, that's it. So same result you will get. Same result you will get for RHD. So both attains a not defined value. Both are equal, but not defined value you got. Indeterminate value. Hence, what do you comment on whose differentiability at x equal to 0? That function is not differentiable at x equal to 0. Getting me? Right. Okay. See, like this you people have to check whether the function is differentiable or not at x equal to a. So like many more applications are there. In my next video, I explain you applications based on this differentiability. Okay, but in this class, just now I would like to focus on only complete concept of this differentiability of a function. Okay, so till now we discussed differentiability of this function at a point x equal to a. Next, now I am going to check differentiability of this function over an interval a comma b. This is the given interval and this is the function. Now when do you say this function is differentiable in open interval of a comma b? See, this function is differentiable in this open interval of a comma b if and only if that function is continuous. That function must be continuous and that function is differentiable at every point which belongs to open interval of a comma b. You know the meaning of open intervals of a comma b. A and b, that extreme values are not included into the interval. So, but middle, many more real numbers are there, no? At every point that function should be continuous as well as differentiable. Then that function is differentiable in this interval a comma b. Now when this function is differentiable at closed interval of a comma b, closed interval of a comma b, tell me. So same like previous one, that function must be continuous. F of x is continuous in open interval of a comma b, and that function is differentiable in open interval of a comma b at a. Okay, this is lower limit, this is upper limit of that interval at a. So RHD of the function must be possible. RHD should be possible, should be defined, and yet to be LHD should be defined. Defined means which attains a finite result. This function is differentiable in this interval whenever that function is continuous in the open interval of a comma b, and that must be differentiable at every point which belongs to this interval and at a. So that RHD of the function should be defined. Yet to be LHD of the function should be defined. I hope you have understood. Like this, you people have to check whether this function is differentiable or not in the closed interval of a comma b. And I said to you, this exponential functions, logarithmic functions, trigonometric functions, inverse trigonometric functions, polynomial functions, constant functions, all these functions are continuous in its domain, and also it is differentiable at every point in its domain. Remember, like a standard result. Okay, students? And sometimes, so for the graph of a function, in some places you may get a vertical tangent. Vertical tangent. Actually, what is meant by differentiation? Slope of a tangent, no? So sometimes you may get a vertical tangent. Wherever vertical tangents are existing, slope of a vertical tangent does not exist, means not defined. Okay, so you know that. So that vertical tangent will make 90 degrees inclination with the x-axis. Then as you know, m is equal to tan 90, not defined. Hence, wherever the vertical tangent is existing, so at that place, so that function will not be differentiable. Okay, I hope you have got it. Okay, so sometimes you get like this graph of a function. Either it may be increasing or you may get decreasing. So here, this is vertical tangent. Vertical tangent you may get like this. If you find left-hand derivative for this, it is going down, means it attains minus infinity. If you find right-hand derivative, it attains positive infinity. Both are not equal, both are not getting a real number. Hence, this is not differentiable. Actually, no need to check all this. Just if the slope is not defined, then you can comment as that function is not differentiable. In this case also, if you find left-hand derivative, okay, so it is attaining a positive infinity. Here, right-hand derivative, it is attaining a negative infinity. Here, left-hand derivative negative infinity, right-hand derivative positive infinity. Here, left-hand derivative positive infinity, right-hand derivative negative infinity, because tangent is going down. So hence that function is not differentiable. Wherever vertical tangent is existing, at that place that function is not differentiable. And also for some functions, if you see the graph, you may get like this. See, for example, f of x equal to mod x function. You know, it is defined on the entire real number set. If you draw whose graph, you will get, see, you will get V-shaped curve. It is meeting the x-axis at 0, 0. Where domain value is 0. At that 0, this function is continuous but not differentiable. Because, so you can remember like a standard result. So for the graphs, wherever these sharp edges are getting, at that place, that functions are not differentiable. Because at this place, if you draw the tangent, one is getting like this, one more is getting like this. Both should be coincident. Whichever tangent, whichever secant is coming from left side and right side, both are coincident at P. In the beginning of this class, we have seen in the graph. But in this type of cases, both will not be coincident. Whichever secant is getting from left side and right side, both will not be coincident. Hence, both slopes will be different. Hence, that functions, okay, those functions will not be differentiable at sharp ends. See, for example, this is a well-known function to you. At 0, you are getting a sharp end. Hence, that place, that function is not differentiable. For example, one more application. See, f of x equal to mod sin x. Now, draw the graph of this function. Draw the graph of this function. X dash, y dash. This is origin. Now this is 90. This is pi. Now 3 pi by 2. 2 pi. Minus pi by 2. Minus pi. Minus 3 pi by 2. Minus 2 pi. Now here it is 1. If you draw the graph of mod sin x, so you know, it attains maximum value 1 when x is 90. So it reaches down pi. So it will not go below the x-axis because mod symbol is there, always positive. So you get again like this. At 270 it attains 1. Again it will go like this. Here attains at minus 90 it attains maximum value 1. It comes down. So it go like this. Now where you are getting at sharp ends? At these places. When x equal to n pi, you are getting sharp ends, where n belongs to integer. Wherever sharp ends are getting, there you draw the tangent. One is coming like this, one more is coming like this. Both are not coincidenting. Hence, both slopes are different. LHD will get a negative slope, RHD will get positive slope. Because LHD is making obtuse angle. RHD is making acute angle with x-axis. Hence, this slope is negative, this slope is positive. Both are not equal. Hence, this is not differentiable. No need to check like this. Because I am a faculty. Being a faculty, I have to give you the clarity. So that I am giving you this much of explanation. But you no need to check like this. Wherever the graph of the function is getting sharp ends, at that points that functions will not be differentiable. You can remember like a standard result. So this type of functions will not be differentiable at sharp ends. For these graphs, where you are getting sharp ends, at x equal to n pi. See, for example, see this function. This is also well known to you. F of x equal to sin inverse of sin x. See the graph of that function. Okay, it is a periodic function which you learnt in the reverse geometric functions. See, x dash and y dash. This is origin. So this is minus 90, this is plus 90. So here it is pi, here it is 3 pi by 2, like 2 pi and so on. Minus 2 pi. Here it is 1, here it is minus 1. You know the graph of this periodic function. You get like this, a straight line. Minus 90 to plus 90. And a plus 90 to C, you get like this. Again it will go like this. See. So if this graph lies between minus 1 and 1, you know. Where you are getting a sharp ends in this graph? At odd multiples of 90. See, at 90 it reaches a maximum value 1. Here you got a sharp end. And at 270. And here minus 90. And here minus 3 by 2. Minus 3 pi by 2. So wherever sharp ends are getting at that points. Where are that points? Minus 3 pi by 2, minus pi by 2, pi by 2, 3 pi by 2. Which means that odd multiple of 90. You know the standard form of odd number. 2n plus 1 into 90, where n belongs to integer. At these odd multiples of 90, that function will not be differentiable. Okay? So same function, sometimes they will write here modulus symbol. Inside, mod if they kept, so this downside, so this graph will not come, it will go like this. See here. Because inside, never be negative. Because I kept a mod, so it will go like this. Now where you are getting sharp ends? Minus 3 pi by 2, minus pi by 2, pi by 2, 3 pi by 2. Okay, students. So now, what do you have to say? X equal to n pi by 2. See, here you got one sharp end. Here you got one sharp end. Here you got one sharp end. Sharp ends. What are the sharp ends? X equal to n pi by 2. If you put n equal to 1, you get this. If you put n equal to 2, you get this. If you put n equal to 3, you get this point. These are sharp ends. At that places, that functions will not be differentiable. Okay, students? Right. Like we have some standard results. See, f of x equal to mod x minus 3 by x minus 3. Is this differentiable at x equal to 3? Check, discuss the differentiability of this function at x equal to 3. Actually at x equal to 3, this function is not continuous. You know, mod of x minus 3 definition, it is going to be x minus 3 if critical value of this function is 3, more than 3. This is going to be minus of x minus 3 if x is smaller than 3. Now find the left hand limit LHL. So limit x approaches to 3 minus left hand limit. So means x value is smaller than 3. Smaller than 3 means this has to be taken. Minus of x minus 3 by x minus 3. Both of them cancel, minus 1. In the same manner, if you find right hand limit, so limit x approaches to 3 plus. So x minus 3 by x minus 3. Both of them cancel, 1. This is minus 1, this is plus 1. Both are not equal. Hence, this function is not continuous. If it is not continuous, obviously not differentiable. See, one more function. See the definition of the function. F of x equal to x into sine 1 by x. If x is not equal to 0. This result is equal to 0 if x equal to 0. Now discuss the differentiability of this function at x equal to 0. Discuss the differentiability of this function at x equal to 0. Shall I discuss? See students, actually whether it is continuous or not at x equal to 0 means, how did you check in the continuity? So this is a bounded function. Sin 1 by x, whose boundaries are minus 1 to 1. Range of sin x is minus 1 to 1, no? Before that x is there. Multiply these three with x. X sin 1 by x less than or equal to x. Now is this continuous at x equal to 0 means put this for left hand limit, take this and put 0. It is going to be 0. For right hand limit, take this function, put 0. So both left hand limit attains 0, right hand limit attains 0, value of the function 0. So 3 are equal and it is continuous. But is this differentiable? No. Because for LHD, you can take this function f of x equal to minus x and do the derivative f dash of x minus 1. And for RHD, so f of x equal to take this function x and do the whose derivative f dash of x minus 1. LHD you got minus 1, RHD you got 1. Are these equal? Not equal. Hence this is not differentiable at x equal to 0. You can think like this. Otherwise you can confirm like this. This is not differentiable at x equal to 0. Otherwise, so you can think like this. See, whose boundary is x less than or equal to x sin 1 by x less than or equal to x, you know. Now, draw the graph of this function. How do you get means? See, x dash, y dash. So, draw the graph of this y equal to minus x. Take this is y. Now, y equal to minus x graph you get, y equal plus x graph you get. Take this is y equal to x. This is the graph of y equal to x. Now, draw the graph of this y equal to minus x. You know, now draw the graph of this. So, you get like this. You get the curve like this with high range of frequency. You know. So, if you draw the graph of this, you may get like this with high frequencies. So, here, this function range is not attaining a fixed value. So, it is oscillating like this with high frequency, not reaching a particular real number on the y-axis range. These are domain values. Now, range see here, changing continuously, no? Not attaining a fixed value on y-axis. So, it is oscillating with high frequency, not attaining a fixed value on its range. Means we cannot comment on the range of this function. Okay, students. Hence, okay, what do you want to comment on the differentiability of this function? It is not differentiable at x equal to 0 because this is 0. So left side of 0, right side of 0. This graph is, okay, this function is reaching different values. Hence, what do you have to comment? That function is not differentiable. So this point is also called oscillating point. Oscillating point or oscillation point. Okay, at oscillating point that function will not be differentiable. Okay, students. So very important okay, application. So sometimes see they will write here n. N belongs to any natural number. So n means any real number you can take. If n is more than 1, that function is continuous as well as differentiable. When n is more than 1, whether it is differentiable or not, continuous or not, I will check. So for example, if I put n equal to 2, then that function will become x square sin 1 by x. Now, sin 1 by x less than or equal to 1. Now multiply on both sides with x square. X square sin 1 by x less than or equal to 1. Sorry, x square. Now, it is continuous at x equal to 0. Where we are checking whose continuity at x equal to 0. At x equal to 0, if you put here left hand limit 0, right hand limit 0, value of the function 0, hence it is continuous. And what about use differentiability? For left hand derivative, differentiate it, minus 2x, put x value 0, going to be 0. For right hand derivative, do the derivative and put x 0, it attains 0. Derivative is done and substitute this x value here, which becomes 0, which becomes 0. 0 is a finite value, it is a real number. Left hand derivative 0, right hand derivative 0, and it is continuous. Hence this function is differentiable when n is more than 1. When n is 1, just now we have seen, that is not differentiable. If n is 0 to 1, if n is suppose 0 to 1, 0 to 1 means you can take like this, smaller than 1, you can take 1 to 0, 1 to 0, at 1 to 0, this function will be continuous but not differentiable. When you take any value 0 to 1, 1 is included, 0 is not included. Take any value and that function will be continuous but not differentiable. If you want, you can check by putting n equal to 1 by 2. Already I kept n equal to 1, I checked. This was continuous but not differentiable. Am I right? Now if you want to take n equal to 1 by 2 and check it. So you get like this. 1 by 2 less than or equal to x power 1 by 2 sin 1 by x less than or equal to x power 1 by 2. Now continuous, because left hand limit 0, right hand limit 0, value of the function 0, continuous but not derivable, because if you do the derivative of this, minus 1 by 2 x power minus 1 by 2, right hand derivative 1 by 2 x power minus 1 by 2. So this comes to the down, minus 1 by 2 root x. This comes to the down, 1 by 2 root x. If you put x 0 here, it attains minus infinity, it attains positive infinity. Both are not defined case you are getting. LHD and RHD both are attaining indeterminate values. Hence this function is not differentiable when n belongs to closed interval, 0 to open 0, closed 1. Open 0, closed 1. Open 0, closed 1. In this interval, this function is continuous but not differentiable. If n is smaller than 0, that function will not be continuous as well as differentiable. If you want, you can check. Take n is minus 2. Then that will become minus x whole power minus 2 less than or equal to x power minus 2 sin of 1 by x less than or equal to x power minus 2. So here it is going to be 1 by x square. It is going to be 1 by x square. For left hand limit, you would have to take this function, put 0, not differentiable, not continuous, because attaining not defined. LHL is not defined, RHL is not defined. Hence it is not continuous, then it will not be differentiable. Okay students, I hope you have understood this concept of differentiability of a function at a real number and over an interval, and also I gave you some standard results. So in my next class of this differentiability, so I will concentrate on applications which are related to the mains and advanced level problems. Okay, thank you one and all.